All right, we're ready to move on, and we're ready to move on with the analysis of our single degree of freedom modal equations for both the time exact as well as the time discrete problem. Okay, so we're going to look at these two modal equations, right? Single degree of freedom modal equations. Okay, so we have here our single degree of freedom modal equations, right? I've used an abbreviation for equations here. All right, we have for the time exact case we have d dot L plus lambda L dl equals 0. Okay, now an ODE is not complete without its without what? Initial conditions, right? So the initial condition that we have here is the following, right? This is after all an ODE for our Lth coefficient in the modal expansion, right? So the initial condition that we have is simply the following. It is that dl at 0, okay, is obtained as psi L dotted with m d at 0, okay, which is of course psi L dotted with m d naught, okay, and just for convention, let's call this quantity, right? Let's call that quantity d0 L. Okay, that's the initial condition. Okay. All right, time discrete. Right, the time discrete case is the following. It is dl n plus 1 times 1 plus alpha delta t lambda L minus dl n 1 minus 1 minus alpha delta t lambda at L equals 0. Okay, and again this holds. How do we bring in the initial condition in this case? We just say that we're given that that quantity we had identified for the time exact problem. All right. Okay. Now, one thing I want you to note is that the way we arrived at this time discrete single degree of freedom modal equation is by starting from the time discrete matrix vector equation and applying modal analysis, modal decomposition to it, right? We could equivalently have gone the other way around, right? So we could have equivalently taken the modal single degree of freedom modal equation for the time exact case, right, which is this one, and then time discretize this. Okay, if we do this, and it's a very, very useful exercise, it's actually a very simple exercise, you would end up with this. Okay, so this remark I'm just going to give you in the form of a sort of flow chart. Okay, so what we have done here is the following, right? We have at one end the time exact matrix vector equation, right? With this is md dot plus kd equals 0. Okay, and I'm going to put a box on it here. Okay, that is md dot plus kd equals 0. Okay. Now, one way of looking at what we did was we went from here down to our time discretized case, right? Right, and this is the following: m d at n plus 1 minus d at n, okay, divided by delta t, right, plus k dn plus alpha, right, equals 0. Okay, so this is the time discrete matrix vector equation. Okay, what we did then is two things. From md dot plus kd equals 0, we went to our single degree of freedom, SDOF for single degree of freedom, modal equation. Right, this is the time exact version, right? Right, which is essentially dl dot plus lambda L dl equals 0 plus initial conditions, right? Everywhere we have initial conditions. Okay, and then what we also demonstrated is how we can go from here to our single degree of freedom modal equation, right? But this is the time discrete case. Right? Which takes on the form that we've written just above here, d L n plus 1 plus alpha delta t lambda L minus dn at L 1 minus alpha delta t lambda L equals 0. Okay, that's where we are. The one step we haven't taken, and which is very easy to take actually, is this one. You could start out with our single degree of freedom modal equation in the time exact form and essentially do a time discretization of it. And indeed, you do get this. Right? Okay, we've done everything but that last dashed the step corresponding to that last dashed arrow. Okay, it's very obvious why this works. Do you know why this? Do you recognize why this works? That's right, because the process of time discretization as well as the process of modal decomposition are essentially linear operations. Okay, and therefore in this sort of setting they commute. Right, those two operations commute. Okay. All right. Okay. It of course not all linear operations commute, but because of the nature of the sort of operations we're carrying out here, they do indeed commute. All right.